pancreas, the endocrine pancreas, and a little bit about the GI tract. Okay. Now, what's causing this picture on the right to look like that?
Focus.
No. One of the side effects of diabetes can be glaucoma, and this is what it looks like with glaucoma. Okay. Okay, so what we're going to talk about today is the endocrine pancreas, and basically the hormonal function, you know, is in the aisles of Langerhans, which are the anatomical units, and there, see right here, they're clumps and clusters of cuboidal type epithelial cells with a lot of vascularis, they're typical endocrine, and they're surrounded by the exocrine portion of the pancreas. But by far they get the most blood supply. Okay? Now, as far as there are species variations in what the islets look like, you can see the human, you can see the monkey, the equine there, and the monkey is very hypercellular, and the cells are much smaller than they are in some of your other species for some reason. They never figure out why, but that's one of the things you'll see. But basically, no matter what the species, they have the same functions and the same cellular content as far as the different types of endocrine cells. As far as the islets are concerned, as we said, they're composed of clumps of cells, and they're richly supplied by your capillaries, and basically those capillaries are very close to fenestrated capillaries, so again it facilitates getting the hormonal secretions into the vascular system. Okay, as far as the vascularity, they basically, even though they're only about 1 to 2% of the mass of the pancreas, they get up to about 15% of the total blood supply that goes to the pancreas. So you see, proportionally, they get a very high level of blood coming to them. Now, they're basically innervated as far as these islets by parasympathetic and sympathetic neurons, and those nervous systems will modulate the secretion of both insulin and glucagon. So not only is it blood glucose levels that causes these regulations, there's also things like that. Okay? If you think you're hungry, what happens to your GI tract? You start secreting and all that kind of thing, and so that can falsely alarm your pancreas to get ready for glucose to come in. Okay, and it can be aggravating if you have diabetes already, because that can be a problem. Okay, there are 4 main cell types that they have identified in the islets, mainly by histochemical staining. Your beta cells, those are the most numerous, and they secrete the insulin. Your alpha cells, the second most numerous, and they secrete glucagon. Your delta cells produce somatostatin, and your F or PP polypeptide cells produce pancreatic polypeptide. Okay. Now, as far as the differentiation of the islet cells, they're not really randomly distributed within the islets, and that the beta cells usually occupy the central portion, and they're surrounded by a rind of the alpha and the delta cells. The PP cells are very rare, usually. And secretion stain with H and E, you can't tell one cell type from another. They all look the same. So you have to use special stains or immunohistochemical staining to identify the particular cell types. Now, why would you want to identify the particular cell types? Well, if it's a tumor, you want to find out which kind it is? And that's what you're going to use that for. This is just showing you some of the differentiation staining here. If you look at the first one, you've got beta cells that are staining alpha cells. You can see the different staining properties. The alpha are staining with the stain. You've got some immunoperoxidase up there for insulin at the top, and also your anti-insulin or anti-glucagon, so you can see some of the different distributions as far as the cells are concerned. And again, we don't use it routinely, but we would use it if we're trying to fully evaluate the pancreatic function as far as the islet cells are concerned and what type of metaplastic processes we may have. Now, as far as insulin is concerned, it is a polypeptide. So where is its receptors? On the cell membranes, right. And it's synthesized, as we said, by the beta cells. It's a relatively small protein, only has about 6,000 Dalton weight. So is it going to hang around in the blood real quick, a long time, or will it go out through the glomerulus and everything else relatively quickly? And would you want it to hang around for a long time? No, it can cause serious consequences such as hypoglycemic shock and death. Okay. Now, it's composed of two chains, an A and B chain. They're held together by two disulfide bonds, so they're bent. And they have an additional disulfide bond within the A chain. And the A chain is 21 amino acids, the B chain is 30 amino acids in length. And there is some species differentiation between the sequence of amino acids, but it's very minor usually. So basically that means that we can use other species insulin to treat different species, which comes in handy in that if we had to use human insulin all the time, then it would be more expensive. So we can use different ones. The one's not too good is sometimes porcine insulin doesn't agree with some different species. But that way we can get the cheapest one that's going to be effective by having that advantage. Okay, this is just showing you the chains right here and how they're held together by the bonds. You can see the one at the top is the excuse me, beta cell and how it's held together right there. And as far as its synthesis, the beta cells will generate the proinsulin, and that consists of basically 3 domains, which you can see the different colors in the top one. Those are the 3 different domains as far as these chains are concerned. We have an amino terminal B chain, a carboxyl terminal A chain, and a connecting peptide known as the C peptide. When you get into the endoplasmic reticulum, the proinsulin is converted to your insulin, your mature form of insulin. You can see basically what happened is it excites the C peptide, and so the top, this right here, the green and the blue is the mature, or the end of that's insulin right there, okay? Now, as far as its release, when the beta cell is stimulated, insulin is secreted from the cell by exocytosis and diffuses into the outlet capillary blood. And what's essential that in order for this excretion to occur, what mineral is necessary? Calcium. Calcium has to go into the cells to cause the movement of the vesicles so they can fuse with the cell membrane and release their substances. Insulin is generally secreted primarily in response to elevated blood glucose concentrations, and glucose is transported into the beta cell by facilitated diffusion through an insulin-independent glucose transporter. Why do you want it to be independent to get into the beta cell? I mean, if the glucose is supposed to stimulate the beta cells to secrete insulin, do you want to have insulin present to get it in there to do that? No, so it's a facilitated diffusion method, and elevated concentrations of the glucose inside that extracellular fluid cause elevated concentrations of glucose within the beta cell. When that glucose comes into the cell, it also activates the calcium pump to pump calcium into the cell from the blood. And so you get that, so you can get it ready to secrete the insulin. Now, elevated concentrations of glucose in the beta cell will cause membrane depolarization, again the influx of extracellular calcium, and this basically triggers the exocytotic process to release the insulin out into the interstitial tissue to be picked up by the blood. Okay? So if I have hypocalcemia, can I have problems as far as diabetes mellitus? Yes, because you can't release the insulin. You have a lot of other problems too, because calcium is necessary to release a lot of hormones. Okay. Now, as far as the glucose secretion of insulin, if you look at the thing right here, you can see you're starting out when we have glucose infusion is initiated. It can be by IV or it could be eating. And notice the glucose spiked, and what did it do? It decreased relatively rapidly, didn't it? And here is normal blood glucose right here. So this is working now, but this should come down like that and then level off. Did it do that? What do you think's the problem with this animal? Got diabetes mellitus. It had a little bit of insulin, dropped it down a little bit, but then what happened? The glucose just went back up again. What usually happens is when you feed the animal, it spikes, it comes down very rapidly below normal, and then glucagon is released, and it goes back up and levels off. In this instance, we didn't have enough insulin to bring it down, so it's causing a problem, right? It's going to happen within minutes. Okay. Now, as far as the regulation of insulin release, when your blood glucose concentrations exceeds approximately 110 milligrams per deciliter, insulin is secreted. So usually anything above 110, they vaguely call that hyperglycemia, although you're not going to see clinical signs usually until you get a little higher than that. Now, when your glucose concentrations go below 60, what's going to happen to insulin secretion? You're going to shut off, because do you want it to go any lower? Or you get hypoglycemic shock. Now, there are other metabolites and hormones that influence insulin release and also its peripheral effects. And these are things like your growth hormone, your various adrenal hormones, and all this type of thing, as far as the glucocorticoids and everything will affect the effects of insulin. So here are some of the factors that affect insulin secretion. You got your direct stimuli. The most important is glucose. But why would amino acids and fatty acids do it? What are amino acids and fatty acids going to be used to make? What's gluconeogenesis? What does gluconeogenesis make? Used to make glucose? Amino acids and fatty acids. And so, if you're doing this, what does that tell in the body you're doing? You're going to raise blood glucose levels. And so that's going to trigger it. Gastrin. Where's gastrin secreted? Stomach. So why would you want insulin to be primed to get ready then? What's that telling you? Yeah, food's coming, right? So get ready, okay? Pancreasymin and cholecystokinin, those are basically, causes contraction of the bile ducts. They call contraction of the pancreatic acid cells. In other words, you're getting everything ready so that when you get the absorption of glucose, because does glucose have to be metabolized by anything in the pancreas, or is it readily absorbed? It's readily absorbed. You don't have to break it down. It's not a complex carbohydrate. It's not starch. So it can be absorbed very rapidly. And so what you're trying to protect the body from is excessive increase of glucose from eating. You all don't eat sugary foods, right?
No.
You don't eat much glucose, do you?
I didn't just
Yeah.
me down.
That's what my grandson tells me, my granddaughter. I said, yeah, Yeah, what happened to all those cookies that were in there on the counter? All that type of thing. Okay. Also, secretin, again, that's one of your digestive enzymes is important. Gastric hormones. Gastric inhibitory polypeptide, glucagon, acetylcholine, all those can cause a direct stimulus of insulin release. Why do we want glucagon to do it? What's glucagon going to do to blood glucose? Raise it. So do you want insulin to get ready in case it goes a little overboard, then they can drop it? And so they work synergistically like that, okay? Indirect stimuli, remember the growth hormone, it inhibits the insulin receptor, and so your glucose is going to build up in the blood, right? And then when it reaches a certain point, it cuts off the growth hormone, and the receptors are open, and then insulin takes that glucose into the cells. Glucocorticoids, remember they also inhibit the insulin receptor. Estrogen, progesterone, they do it through numerous mechanisms. As far as direct inhibition, somatostatin is the main one. Remember, somatostatin inhibits a lot of stuff, doesn't it? And then we have epinephrine, norepinephrine. Why do you want epinephrine, norepinephrine to inhibit insulin? Can't hear you. Well, if epinephrine, norepinephrine, that's fight or flight, right? What has to be getting a lot of glucose to figure out if you're going to fight or flight? The brain. The brain does not use insulin receptors in the majority of the portions. So in other words, you're inhibiting little things like the other, the muscle and the liver from taking all the glucose away from the brain. So that the brain can say, okay, let's get out of here. And once that's doing, then that's going to cause, again, the release, the epinephrine stuff will go down and get the insulin into the muscle so you can run. Okay? And so it's a safety mechanism, protection mechanism. Now, what happens to insulin? Well, what organs do you think metabolize it? Liver and the kidney, because they metabolize the other ones, right? And they contain enzymes that reduce the disulfide bonds that link those A and B chains together. Once they're broken, you'll break down the different the proteins down into the peptides, amino acids by protease activity, and then they will either be excreted or they'll be recycled for use. Now, the half-life of endogenous insulin is only about 10 minutes. And what does that tell you about how powerful it is? The shorter the half-life, the more powerful the hormone is. Okay. Now, the insulin receptor is embedded in the plasma membrane. The receptor's on the surface and has proteins that go through the membrane to take that signal down, right? It has 2 alpha subunits and 2 beta subunits linked with a disulfide bond. You can see them right here. So good. Oxidizing agents mess up this whole process. What do oxidizing agents do to disulfide bonds? They break them, and so you're going to destroy your insulin, you're going to destroy all the receptors and everything else as far as oxidizing agents. Now, as far as the alpha chains, they are entirely extracellular, and that's where the binding receptor is for your insulin. And the beta chains will penetrate through the plasma membrane, and so they're going to take the second messenger effect down in there and get the, whatever the cells needs to pump that glucose in there and get to work as far as giving you energy for your cellular metabolism. Now, the insulin receptor is a tyrosine kinase. In other words, it functions as an enzyme, transfers phosphate groups from ATP to tyrosine residues. In other words, why do you want to get those ATP off there? What's the cell using for energy? ATP. Now, what's a kinase mean? What's A's mean? An active enzyme. What's a kinase? It's an enzyme which cleaves off a high energy phosphate. And what's a high energy phosphate in this case? ATP. Okay, so that's what it's doing. Now, your binding of insulin to the alpha subunits causes the beta subunits to phosphorylate themselves, and that activates a catalytic activity of the receptor. So that activated receptor then phosphorylates a number of intracellular proteins, and then you can use these to basically act as substrates for different things that are in there. Also, you're releasing ATP, so you get energy from them, and all this type of thing. Okay. Now, as far as there are intracellular proteins that have been identified as phosphorylation substrates for this receptor, there is one that's called insulin receptor substrate 1, IRS1, and they're doing a lot of research on that to try to find out if there's some way that they can, alleviate some problems with diabetes mellitus by giving, and basically causing an increase in these receptor proteins in there. Okay, now what's insulin do? What's its main thing to do?
Lower blood glucose.
Well, lower blood glucose, but is it mainly to lower blood glucose, or is it to make sure the cells can get glucose? Right, so the major function is to supply glucose as a source of energy for your different cells. And it's a good side effect that can lower blood glucose, okay? Now, it's a very key player in control of intermediary metabolism because it affects both the carbohydrate and also, remember, the lipids and the fatty acids. Fatty acids. Can you use lipids for energy?
Yeah.
Yes, but they basically have to insulin has to be able to transport them and also get the cells to make them into glucose and stuff. But it also has, influences on your protein and mineral metabolism. In other words, it's not just the carbohydrates, that's its main function. But through its effects upon cellular metabolism and stuff, you can make them also metabolize minerals, metabolize proteins, and all this type of thing. Okay? But the net effect of insulin is to lower blood glucose concentrations, fatty acids, and amino acids, and to promote conversion of these compounds to the storage form. In other words, what's the storage form for glucose? Glycogen. What's the storage form for fatty acids? Triglycerides. And as far as what's the storage form for amino acids? Proteins. And so is this also helping to build up that target cell? Yes. And so basically it's a beneficial effect to basically build the cells as far as giving them energy, but also giving them substrates to be able to multiply and all this type of thing. Now, as far as insulin and carbohydrate metabolism, as we say, insulin facilitates the entry of glucose into muscle, adipose tissue, and several other tissues. What about the heart? Is it a major thing on the heart?
No.
What's the heart used for energy? Glucose or what else? What's the heart mainly used for glucose? Used for energy? If you put a bunch of fat in the heart muscle cell, what are you going to do to its function?
Ketones?
Not ketones. Lactate. Lactate. Okay. Because if you have a cell, heart cell, it's got ample oxygen available, what's going to convert that lactate into? Pyruvate. What happens to pyruvate? Pyruvate goes into the goes to succinyl-CoA and the citric acid cycle. And what's the products from that? ATP and your NAD and FAD and that type of thing. You need all those things to maintain energy levels and metabolism? Mm-hmm. Yes. Well, what if you don't have enough oxygen in that heart cell? What's that lactate going to be converted to? Lactic acid. Is that a very good thing to have in a cell? Can it damage the cell? Right. Y'all, and you know about tying up syndrome, right? Y'all know what tying up syndrome is?
No.
Tying up. How about exertional rhabdomyolysis? What's rhabdomyolysis mean? Breakage of striated muscle. Okay, so those common in horses. And what's the situation that leads up to it? No? You know about Monday morning disease? In other words, racehorses are usually in very good condition, so they have a very high level of oxygen in their muscles. What about this horse? This owner has this horse and works all week, and the horse sits around in the stall or the pasture doing nothing but eating. Goes out there on the weekend and runs that poor old horse into the ground, sticks him back in the stall, and goes back to his house. What's going to happen to that horse over that time? In other words, when it went out there, did it have much oxygen in that tissue available for pyruvate? Or was it mainly anaerobic and it got converted to lactic acid? And lactic acid sits in those muscles and starts eating away at those muscles. So you get myoglobinuria, you get myoglobinemia, you get renal failure and everything else if that keeps up. Okay? And that's because of the inadequate amount of oxygen to properly metabolize the energy sources as far as those muscles are concerned. Okay? Y'all remember that from biochem? Didn't we have a little bit of physiological chemistry last year? Don't tell me you didn't have it in there, because I taught it to you. So. Okay, now the only mechanism which cells can take up glucose is by a facilitated diffusion through a family of your hexose transporters, and they're called GLUTs, G-L-U-T. Okay, now some of these